So, hello everyone. I'm Owen Hilliard. I'm one of Alexi's PhD students. Today I'm going to present Taking Out the Trash, Maximizing Transactional Cache Hit Rate. So, the motivation behind this paper is that in a transactional system, if you submit a batch of requests to a cache and it's missing one of them, for instance, in this case, the cache is missing C, it has to go to the database, get C, and then it can give you everything else back, which means you haven't really saved anything over just going to the database for everything, unless those queries are expensive. So the ideal case is everything you want is in the cache, and the cache just sends it back to you and you don't have to talk to the database. So here we have a very simple SQL transaction. We have a table A, and we grab some data from it, and we use that to do some selects from tables B and C, and then we use some data from C to get D. And that forms this tree of data dependencies. So for the purposes of this paper, we're focusing on the critical length, which is the number of sequential accesses on the longest non-cached path, lower being better. So if you do a depth-first traversal and you only count uncached items, that's the critical length. So then there's the individual transactional hit rate, which is it's a percent reduction in critical length for a given transaction and a given cache configuration. And then there's an overall one, which is for a given starting cache and then transactions which can transform the cache, how well does it do in that state? And all of these are important metrics for evaluating a cache for a transactional system. So, for example, here, if we have nothing in the cache, the longest uncached path is A, then C, then D. And we have a critical length of 3. If we cache A, then we only need C and D from the database. We also need B, but that's not on the longest path. If we cache B, it doesn't do anything. So all we've done is wasted space because we still need to get A, then C, then D, so we haven't actually achieved any speed up. If we cache A and B, that's no different than just caching A. Because again, you need C and D, so you've wasted space. Caching A and C, however, you can request B and D in a single request. So this is a good configuration, and adding in B or D doesn't really do much. And if you cache B, C, and D, then you still need to retrieve A, but you can get everything else. And then obviously, if you can cache everything, that's the ideal case, but that's impractical most of the time. So in order to do this, you divide things into groups. So we might group A and B, or C and D, or A and C, or A and D. And each of these have different characteristics as far as what reduction to critical length they provide and how ideal they are for the database. And this is something that you can compute as soon as you know what the transaction looks like. And that is very helpful because even working at a table granularity like this, if you can kind of figure out which tables are more important, that can be information that is used to inform your caching policy. So the way a single group is scored is you look at all the key frequencies and you take the minimum of that and multiply by the number of transactional hits generated. Essentially, you divide how useful the group is to cache by how big it is, which is how expensive it is to cache. So you're trying to optimize for most value per resource spent while caching. And we need to calculate this score so that we have a number that we can plug into existing cache eviction algorithms. So at runtime, we need to generate scores for the individual keys. And here we have very, very high frequency keys. The weight is reduced, but it's very important that if a key has a very high sum of single transaction instance scores, that means it's very important to some transactions. And then there's a global aging factor to help temporarily hot data get evicted. So one important observation is that a lot of times you have transactions which differ only by a single table. And this is very helpful because the previously mentioned approach has exponential complexity both in the number of tables and the number of keys, which is very not ideal. So if you can figure out A, B, and C are a group that I can memoize all these calculations for, you can save yourself a lot of time. And while it's still exponential, it's at least a better exponential. And you save yourself a bunch of work. So the way they implemented this is called Detox, which takes application code, which interfaces with a Java database driver. And at compile time, it extracts the transaction graph with those data dependencies, identifies the possible groups, which is the power set of tables, and then it compresses them for places where groups are more or less interchangeable. And that reduces the complexity of the calculations made at runtime. So at runtime, keys belong to a table, and so you map those key accesses to groups, or you infer all those keys from batch requests that you're getting in which case you can't do all of this at compile time. You have to do it at runtime. So that is a not ideal case for this application. And once you have that, you just do normal caching things. So this results in some very interesting looking results across several benchmarks. So if you look at product group 2, you are able to, using 25% of the cache size relative to data size, get results that would require you to cache 80% of the full data size with other approaches. And there are similar results for other product groups, or it's basically the same. So this is very promising for reducing the amount of data that you have to store in order to effectively cache things. Or use the same cache size and you can do a lot more with it.
Owen, can you go to the previous slide?
Yeah.
This is for a single transaction, right?
Yes.
But we have to do it for all transactions.
Yes.
Okay.
Yeah. All right. So the paper doesn't make it extremely clear whether this information is abstracted and compiled into the cache or whether the cache can be dynamically updated. I assume that is an implementation detail. But they do mention their ideal case is figure out all the transactions at compile time and then have all of that data available and pre-computed.
And the blue edges represent the path if we don't have the application code. Okay, that's at runtime. Okay.
Yeah. Yeah. So in other benchmarks, Detox is generally for instance, for OLTP benchmarks, is either more or less tied with or better than other approaches, which does make this very promising. However, there are some downsides. So although there are optimizations done, the work is still at least O(n) squared. So as the transaction size increases, you have latency growth and you have a drop in throughput due to the extra work that has to happen because you've increased the size of the transactions. Now, it wasn't mentioned explicitly whether these were more tables involved or more keys involved in the paper, as far as I read. However, this does mean that it would be important to test this caching policy for your workload because it suffers from complex transactions. So I have a couple points of discussion, one of which is that it gets most of its performance when it can pre-compute transaction graphs and whether that is realistic. So why don't we discuss that for a bit and then we can move to the next one. And this is kind of end of the presentation, so feel free to stop the recording.